So welcome to all. Myself Dr. Santhosh Singh, working as an Associate Professor in Department of Physics, Institute of Aeronautical Engineering. Today my video lecture topic is Optoelectronic Properties of Semiconductor Material. So first I want to tell what is semiconducting material. So generally all the materials are found in three categories, namely insulator. The second one is conductor. And of course, my course of choice is the third and last one is semiconductor. Okay. So basically all the materials in this universe are lie in these three categories: insulator, conductor and semiconductor. So what is semiconductor? So semiconductor property is in between the insulator and conductor, means the conductivity of semiconducting material is lie in between insulator and conductor, means its conductivity is greater than insulator but less than conductor. Why? That's why the name semiconductor. Okay, its opposite of conductivity, that is resistivity, is even less than insulator but greater than conductor. Okay, so you can define the semiconductor on the basis of three categories. First, conductivity, resistivity, and the third on the basis of energy band diagram. Energy band picture or diagram. So the first two approach is classical approach to define the semiconducting material. And this third one is quantum mechanical approach. Why? Because the energy concept of origin of energy, band gap and all can only be described with the help of quantum mechanics. That's why if you are defining the semiconducting material on the basis of energy band gap, means you are using the quantum mechanics approach or quantum mechanical approach. But conductivity and resistivity normally you can explain with the help of classical physics or classical models. So that's why if you are defining the semiconducting material on the basis of conductivity and resistivity, you can say that we are adopting the classical approach. Okay. So now, what is the conductivity of semiconducting material? So suppose there are one semiconducting material, name A, and its conductivity is sigma. This is what? Semiconductor or semiconducting material. And its conductivity is, let's suppose, sigma A. Another material B, it is the insulating material. And its conductivity is sigma B. And another class of material C, that is conducting material, and its conductivity is sigma C. So sigma A means conductivity of semiconductor material will be greater than insulating material sigma B but less than the sigma C conductors. Means conductivity of conductors will be always high if you are comparing with the insulator and semiconductor. Conductivity of any conductors will be always greater than the semiconductor material conductivity. Resistivity means If you want to define the semiconducting material on the basis of resistivity that represented by rho. So resistivity is nothing but a kind of resistance. So resistance will be always greater for insulator. Okay. Then semiconductor. Then conductor. So this relation, this inequality relation inverse, if you are defining the semiconductor on the basis of resistivity. See, on the conductivity relation, if you are defining the semiconductor material with the help of conductivity, this inequality relation open the mouth in this direction. Means the conductivity of conducting material is greater than both insulator and semiconductor. But in the case of resistivity, the insulator have larger resistivity comparison to semiconductors and conductor. But in both cases, this semiconductor material lie in the middle, means they have the moderate property. All the property lies of the semiconductor in between the insulator and conductor. Okay. Now the next question, why these semiconductors are so important so that we are choosing this material for study or for learning. Why? Because with the help of this semiconductor material, you can fabricate the many electronic devices, okay, which are very helpful for any device application. Electronic devices are, and that devices are very helpful for any technological application. Like you can design the PN junction diode, field effect transistor, and many MOSFET, many type of semiconductor device you can design with this semiconductor material, and that device will be very, very useful or applicable for modern day technological application. Okay. So that is the importance of semiconductor material. With the help of semiconductor material, you can fabricate or you can design or you can build the semiconducting devices, and that devices will be very, very useful in modern day technological application like diode or solar cell or light emitting diode, okay, or MOSFET, FET, okay, all will be useful for modern day technological communication industry. Okay, so this is the primary picture for semiconductor material. Classical primary picture for semiconductor material. Why? Because I define the semiconductor material on the basis of classical approach. Okay, on the basis of conductivity and resistivity. Okay, now how you can define the semiconductor material with the help of quantum mechanics? So quantum mechanics believe the discrete sets of energy level of any atom, and if you if you are considering the solid, means if you are considering the number of atom, so the energy atom of all the number of atoms will build the kind of bands, and that bands will be classified as a two category. One is valence band and the second one is conduction band. And energy difference between these two bands is known as energy band gap value, that is denoted as Eg. Okay. So with the help of this Eg, you can classify the semiconductor or insulator or conductors. How? As you know, the conduction band and valence band is overlapped for the case of conducting material or conductor. Means Eg is equal to 0 for the case of conductor. And also you know that the conduction band, difference between the conduction band, the difference between the valence band and conductor. Lower band is always known as valence band. So the difference between the valence band and conduction band in the case of insulator is nearly around 4 electron volt or 4.5 electron volt. Greater than 4.5 electron volt, or you can say started for 4.5 electron volt, and even higher energy difference is also considered as an insulating material. Even it is generally it is started from 4 electron volt, but sometimes this 4 electron volt range is considered as high band gap semiconducting material. That is also applicable for many device applications. That's why I don't want to take these value. That's why I started for 4.5 electron volt. So all the energy band gap, all the material which energy band gap value is greater than 4.5 electron volt is considered as an insulator. Okay. Here in the case of conductor, you are able to see that there is no energy band gap. Here the energy band gap is very large, even larger than 4.5 electron volt. Okay. So this is insulator. This is conductor. Now semiconductor energy band diagram. See, this semiconductor have energy band gap value, but greater than the conductor, because in the case of conductor there is no energy band gap value, but in the semiconductor there are some energy band gap value greater than the conductor but less than the insulator. Okay, so you can say that the semiconductor have the energy band gap value from 0.1 electron volt to up to 4 electron volt. This 4 electron volt case is also considered as a high energy band gap value semiconductor. Generally, the classical approach is 0.1 electron volt to 3 electron volt or 1.6 electron volt, and 1.6 electron volt to 4 electron volt is considered as high energy band gap semiconductor material. The additional term high energy band gap semiconductor material is required to define the semiconductor material which have the higher energy band gap value from the value 1.6 electron volt. So classically the semiconductor material have the energy band gap value from 0.1 electron volt to 1.6 electron volt. That is the normal energy band gap material, semiconductor material. But 1.6 electron volt to 4 electron volt material is also considered as a semiconductor material, but with the name higher energy band gap semiconductor material. So obviously this semiconductor material also have the moderate band gap comparison to conducting material and less than energy band gap comparison to insulating material. Okay. So this is the quantum mechanical approach to define the semiconducting material. Why? Because with the help of only you can define why the valence band and conduction band arises. If anyone asks what is the valence band, what is the origin of this valence band or conduction band, you can only use, if you want to give the answer, you can answer on the basis of quantum mechanics. That's why this is the quantum mechanical approach to define the semiconductor material. Okay. So this is the basic overview of semiconductor material. Okay. Now, obviously, the in modern day, all the things is dealing with the help of quantum mechanics. So why this energy band gap originated? Okay. Any material, either semiconductor or insulator or conductors, are built with the help of atoms, and that atoms are arranged in a periodic manner inside the solid. Okay. See, I am trying to draw the atom, position of atom. This site are known as lattice point or lattice site. Okay. This where the atoms are situated. So generally all these arrangement of atoms are maintain the periodicity. Means at a certain period or at a certain distance, the atom will repeat itself. Means suppose one atom is here, and after x distance the next atom are found, then again after x distance from this atom, again you will find the next atom. This is known as periodic arrangement of atom. Okay. Suppose this periodicity is maintained in x direction, x-axis, along the x-axis. In y-axis, suppose this periodicity is maintained by some different distance, say b. So in all the possible directions, generally the atoms are maintain the periodicity, while it will arrange in the inside the solid. Okay. And this arrangement or this periodicity arrangement will govern or will be the primary factor for the origin of energy band gap. In quantum mechanics, there is one approach that is known as particle in a box case. So what happened in this case? There is one hypothetical box, and that box have an infinite potential well, V is equal to infinity. And one particle of mass m is trapped inside the box, so that that particle cannot come out from this box. Why? Because this wall have the infinite potential energy. Okay, that's why particle in box, the particle is trapped inside the box. Okay, so this is the quantum mechanical situation or problem. So what will be the energy of this particle inside this box? So there is one formula, En is equal to n square h square upon 2 ml square, n square h cut square upon 2 ml square. Okay, where n is the integer. So this particle have the discrete set of energy. If you are putting n is equal to 1 means E1, so h cross square upon 2 ml square. What is this L? L is the distance, length of this box. Means that this particle can move inside the box within the limit of L. Okay. So energy of this particle in quantum mechanical term is like h cross square upon 2 ml square, or the next energy level will be 4h cross square upon 2 ml square, like that. So what is that? You are finding that this energy are nothing but discrete energy level. Discrete energy level. Oh, if you are plotting the energy level of this particle in a box case, so suppose this is the E1 case, means h cross square upon 2 ml square. Then next case E1, then E2. The next energy, allowed energy is what? 4h cross square upon 2 ml square. Obviously some term will be cancelled here, whatever the thing. Means you are able to see this particle have the discrete energy level. Either this energy level or this energy level. Again, if you are putting n is equal to 3, some more different energy. some different energy level will become. So E1, E2, E3 is in discrete set of energy. Discrete set means after E1 energy, this E2 have some definite value. In between E1 to E2, there are infinite number of energy values exist, but this particle cannot adopt that energy value. Okay? This particle must have either E1 energy or E2 energy or E3 energy. Okay? This is the concept of discreteness in energy, or this is the concept of even quantum mechanics. Every particle must possess discrete set of energy. Okay, so this is the case of single atom. And suppose there are more number of atoms, like a solid case, these energy levels will convert or turn into bands. Okay. These energy levels will convert into bands, not in a single energy level. So the uppermost filled band is considered as a valence band, and the other band above the energy level of valence band is known as conduction band. Okay. The topmost level in valence band is known as valence band maxima, and the minima energy of our bottommost energy level in conduction band is known as minima of conduction band. Valence band maxima and conduction band minima. Conduction band minima and valence band maxima. And difference between these two energy level is known as energy band gap. Okay. So why the bands arises? It is arises due to the presence of number of atoms inside the solid. Why? Because individual atom energy is characterized by the energy levels. Sharp energy level. If there are more number of atoms, these energy level will turn into forming the bands. Okay. And if these bands are fulfilled up to a certain level, then these fulfilled band is known as valence band, and the unfilled band, empty bands, is known as conduction band. Every atoms consist with core part, that is known as nucleus, and electron is moving surrounding this nucleus. So nucleus plus electron is known as atom. An atom. So obviously, what are these? These are the positions of atoms. Atoms are situated here. Means there are one central positively charged nucleus, and the electron is surrounding around these places. Okay. And so all the electrons are charged particle. Nucleus are also charged particle, positively charged, and electron is negatively charged. So that nucleus will also present a kind of potential, and that potential is C. These atoms are arranged in a periodic manner. So the nucleus are also arranged in a periodic manner, and that nucleus will also able to produce the potential. So that potential will be also vary periodically. So whatever the electron is revolving around the atom or try to free or try to move inside the solid or any crystal will experience a kind of periodic potential. Okay. So generally electron will move inside the crystal in periodic potential that is originated from the nucleus. Okay. So that the same thing is written here. The crystalline solid consists of a lattice which is composed of a large number of ionic core. core means nothing but nucleus, at regular intervals, and the conduction electron means free electron or whatever the electron will try to move inside the crystal or solid throughout the lattice. Let us consider the picture of lattice in only one dimension. For simplicity, they are considering only one dimensional case. Only an arrangement of ionic cores along x-axis. Okay. If you plot the potential energy of conduction electron as a potential as a position in the lattice, the variation of potential energy is shown in the figure. Okay, the potential is minimum at the positive ion sites and the maximum between the two ions. Means at the site position the potential is minimum, and once you are moving ahead from the site, the potential is maximum. So see here minimum, then again if you are moving ahead it will be maximum. Once again you are reaching to one next atom, or again if you are reaching to one nucleus, that is core region, again it will be minimum. So a kind of periodic potential will be developed inside the lattice or inside the solid. Okay, so that thing is actually given by the Bloch, and what he suggested, the periodic potential Vx, the potential V, may be defined by the means of lattice constant. Suppose the atoms are situated at a distance apart from each other. So that's why the periodic potential Vx may be defined by the means of lattice constant A, and that potential, you can represent that potential in the term of A, lattice constant A. That's why it will be always, so the periodicity Vx will be always equal to Vx plus A. Means whatever the Vx value, after A distance, the same value you will get. Okay, so that's why this A is what? Period of potential. So for such an electron moving in periodic potential, Bloch considered the eigenfunction or wave function for such conduction electron. So every material particle, a kind of wave is associated, and equation of that wave is known as wave function for that particle. So if the electron is trying to move inside any crystal or solid, a kind of wave is also associated with that electron, and means the wave equation or wave function for that electron is given in term of this periodic potential function, and that is given by a scientist Bloch. And what he suggested, the wave function associated with this free electron or whatever the electron try to move inside the crystal or solid is what? Psi kx is equal to e to the power I kx u kx. Okay, where ukx is the periodic with the periodicity of the crystal lattice and is called the modulating function. So ukx is also a kind of periodic function, and its periodicity you can check as a ukx plus A. Okay, so therefore according to Bloch's theorem, the free electron wave is a plane wave function because the term e to the power I kx is here. So therefore according to the Bloch's theorem, the free electron wave is a plane wave modulated by periodic function ukx, which has the same periodicity as a potential of electron. Okay, so this thing is the given by Bloch. But the concept of periodic potential is not actually given by the Bloch. The new scientists named Cronin and Penning, this so that the actual potential is in this shape. It will be also constant here. In the Bloch case, it is like that. Okay, but see it in this Cronin-Penning model case, where the electron will move inside the crystal or inside the solid, the potential is a kind of rectangular potential. Okay, rectangular potential. So, okay, the periodic potential assumed by the Cronin and Penning is shown in the below figure or this figure, a series of rectangular walls of width A and are placed at the separation of B, okay, in the region where x is greater than 0 and less than A. The potential energy is 0 and the region such as minus B, x is greater than minus B and less than 0, the potential energy is V naught. Okay. So means here the potential value, here or here, this maximum potential value is V naught and here the potential value is what? 0. So it is a kind of a step function. Either potential is 0 or V naught. Okay. But in previous case, which is given by blows, see, at each and every point inside the crystal or inside the solid, the potential is varying. Okay. The potential value is not fixed. So it is very, very difficult to solve or draw the conclusion for previous case. And to overcome that difficulty or that situation, Cronin and Penny, one scientist, suggest a new kind of model, a new kind of model potential which is present inside the crystal. And that potential is constant or step kind of potential that is known as rectangular potential also. Okay. So one dimensional periodic potential, that kind of potential is also known as one dimensional periodic potential assumed by Cronin and Penny. And what is this? This is a kind of constant potential in certain region. In this region, the potential value is V naught. Again, it will be 0. Again, in this region, the potential value is V naught. Okay. So either it will be V naught or 0. No in between value like that. Which is considered by Bloch in previous case. So what is the effect of considering such type of potential? It will be easy to solve the many problem. Okay. The last approach or that approach which is given by Bloch is not applicable or it is very, very difficult to solve. Okay, once you are trying to solve or if you are trying to find out the many physical quantity while using such type of potential, it is very, very difficult to get the solution. So to overcome such situation, the Cronin and Penny suggested a kind of constant potential. That potential is also known as rectangular potential or step potential. Okay. Okay, now the origin of energy band formation in solid. I already gave some basic introduction how the band origin energy bands are originated in early discussion. So see here, once the two atoms, there are two energy levels. One the three atoms, here three energy levels. If there are n number of atoms, as in the case of solid, these energy levels are now closely spaced. And what you call, if you are seeing this picture, comparison to this picture is clearly suggested this is energy level. Now see this picture. If this energy level are so closely spaced, this energy level are known as energy bands. Okay. So why this energy bands appear? Because due to the more number of atoms present in the solid. If there are two atoms are single atom, there only two levels are single levels. If there are three atoms are present inside the solid, there are only three levels. If there are n number of atoms present in the solid, which is the actual case, if you are considering suppose carbon, if you are taking 12 gram carbon, means 1 mole carbon, how much atoms, carbon atom are present there? 6 into 10 to the power 23, Avogadro number. 6.023 into 10 to the power 23, Avogadro number. So even if you are choosing 12 gram carbon, this much number of electrons or atoms are present. Okay, so even if you are choosing a small amount of solid, too many huge number of atoms are present, even such a small amount. So if you are representing the energy level of all the atoms which are present inside the solid, that energy level will be always appears as a band. This is the primary reason. So the same thing written here, when we consider the isolated atom, the electrons are tightly bound and have a discrete sharp energy level. When two identical atoms are brought closer to the outermost orbit of these atoms, overlap and interact, the more atoms are brought together, more levels are formed, and for a solid of an atom, each of energy level of an atom is split into n levels of energy. The levels are so close together that they form almost continuous band. Okay? The width of this band depends on the degree of overlap of electron of adjacent atom and is greater for outermost atomic electrons. So based on these, how the energy bands is originated inside or originated for any solid or any kind of material. The energy bands in the solids are important in determining many physical properties of solid. The allowed energy bands is known as valence band or conduction band. I already told in early discussion. The band corresponding to the outermost orbit is called conduction band. Okay, means that band is empty. Okay, there is no electron, or if there is an electron, that electron is considered as a free electron. Okay, so the band corresponding to the outermost orbit is called a conduction band, and the next inner band is called valence band. The gap between these two allowed bands is called forbidden energy gap. Okay, so already I drawn in my early discussion this side. On the basis of band theory, width of forbidden energy gap, solid can be broadly classified into three categories: insulators, semiconductors, and conductors. So see, in the case of insulator, this energy band gap or forbidden gap energy is large comparison to all other case, means in the case of semiconductor or with conductors. In conductor case, there is no forbidden energy region, means no gap. Eg is 0 here. Here Eg is too large. Here Eg is somewhat but greater than the case of conductor, but less than the case of insulator. So on the basis of this energy band diagram, you can classify the material in three forms: insulator, semiconductor, and conductors. Semiconductor material have some energy band gap value, but less than the insulator, but greater than the conductors. Thank you. Thank you for all.
Like, share and subscribe. Hit the bell icon for more updates.